How's it going, everyone? We'll get started in another minute or two here. If you're in chat, can I get a quick thumbs up if you can see my tablet screen right now? Okay, perfect. Did you want me to get started now, Drews? We only had only about 50 people in here, 55 people. Okay, perfect. Okay, so today, as Dr. Drews mentioned last Wednesday, we're going to be talking about reversible reactions. Now, a couple of things I did want to sort of reiterate before we got started on that Dr. Drews covered last class was that the general form of rate laws for reactions is going to look, or rather a reaction that is of the form A times A plus B times B goes to C times C plus D times D. The general form for the rate law of this sort, at least for species A, is going to look like K, or excuse me, not species A, just the rate law is going to equal KCA to the power of A times CB to the power of B. Now, there was a question last lecture stating that in this particular case, the rate law is only dependent on the reactants, and that is true. However, for reversible rate laws, we're going to see that that is not the case, and it will be dependent on both the reactants and the product. So generally speaking, for an equation of a similar form, except instead of a irreversible reaction, we'll be looking at a reversible reaction. So we'll have a double arrow. We'll find that the rate law here is going to be equal to the rate of the forward reaction minus the rate of the reverse reaction. Now, in this particular case, sorry, one second, I'm trying to get my windows out of the way for my notes. Now, in this particular case, this equation is going to be I believe 315 in your book. And what this allows us to do is we can look at reversible reactions as two distinct reactions, essentially a forward reaction and a reverse reaction. So I'm going to, at least for now, I'm going to be subscripting some of our variables with F and R for forward and R for reverse. And so if I were to write this as two separate reactions, I can write it as this. So A and B react to form C and D. And I could also write a reverse reaction that's going to look like C and D react to form A and B. Now, independent from each other, each of these has their own rate constant that I'm going to label as Kf and Kr for forward and reverse. And now using equation 315, we can sort of get an idea of how, using 315 and sort of the rate law up here that describes a general rate law, we can sort of describe what a reversible rate law is going to look like. So in the case of a reversible reaction, we have a rate law that is of the form R is equal to Kf times Ca to the power of A, Cb to the power of B, minus the reverse reaction, which is going to look like K sub R, C to the C, C sub C to the power of C, and C sub D to the power of D. So in this case, we have a forward and reverse portion that define the overall rate law for the reversible reaction. And one other thing to note here is that this Kf and Kr, typically we don't want to have to deal with a forward and reverse rate constant. So we have what we call Kc that we use to define as the ratio between these two. So this Kc is defined as Kf, the ratio of Kf to Kr. And putting this into the equation gives us a form of Kf times Ca to the power of A, Cb to the power of B, minus C to the power of C, and the concentration of D to the power of its stoichiometric coefficient, all over Kc. Here, Kc is, we call it the equilibrium constant. And this is distinct from Ka. So previously we defined Ka also as an equilibrium constant. But there's a relationship that we're going to go over by the end of this lecture that relates Kc to Ka, but they are not directly equivalent. As of right now, you can consider Kc as simply the ratio of the forward rate constant to the reverse rate constant, and Ka is sort of the thermodynamic equilibrium constant. Okay, so here we have a fairly general form of what the rate law for a reversible reaction is going to look like. And let me highlight this one for you. I don't know why I boxed it. I just did that out of habit when I have a highlighter. I also don't know why Dr. Drews likes coloring these in, because I find this incredibly tedious personally. Okay. So here we have the general form of a rate law for a reversible reaction defined using Kc. Another thing that I wanted to point out here is that Kc is defined as the equilibrium constant, and it's only defined at equilibrium. So if you recall, in a equilibrium is defined as when the forward reaction is equivalent to the reverse reaction. So that is that's RR or RF. The rate law going forward is equal to the rate law, the reverse rate law at equilibrium. So question, the exponent on the D concentration should be lowercase d. That is correct. Oh my God, I just deleted all of that. Yes, this should be a lowercase d, sorry about that. And so let me re-highlight all this. Apparently, if you erase any portion of the green, it deletes your entire highlighting. Okay, yeah, that should be a lowercase d. So as I mentioned, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. This is important to note that, as previously mentioned, when you're at equilibrium, the reaction doesn't stop. It just means that the transition from reactants to products and products to reactants is equal in speed or in rate. And so at equilibrium, we can define this as KF. We can define, we can use this sort of relationship to define Kc as the concentration of C to its stoichiometric coefficient times concentration of D to its coefficient divided by concentration of A and concentration of B to their respective coefficients. So this equation here is going to be 320 in your book. And another form of that, I should before I write that, another form of this equation generally can be written as concentration of a species to its stoichiometric coefficient, where you're taking the product of all of them from species A to species Z. So this here is equation 320 in your book. Definitely increase the width of my highlighter so I don't have to make this so tedious for myself. Okay. And so now using this sort of information here, we can define a rate law for a reversible reaction, and we defined a Kc. So we can work through an example real quick of how you would sort of deal with these. Now, keep in mind that Dr. Drews, as previously mentioned, had said that sort of a lot of these steps that we're doing here, when we get to more complex problems using and looking at CSTRs and batch reactors and whatnot, these are sort of just going to be the intermediary steps. So these examples are going to be relatively simple today, although I probably shouldn't call it simple because, as Dr. Drews said, nothing is simple the first time you see it. But they'll be doable. So question, does R sub F and equal RR mean that the reversible, that R reversible is equal to 0? So not quite. It just means that they're equal to each other. It doesn't mean that they're 0. So as I was saying, if you have a system at equilibrium, that just simply means that the rate of the forward reaction and the rate of the reverse reaction are equal, not that they're 0. Because if they're 0, then the reaction stopped. But it's just that the switch between product and reactants are equal. Okay. So example. So given a reversible reaction of the form 2A plus B goes to C plus 3D, I want to know, find the rate law, the rate for individual species, RA, R sub B, R sub C, and R sub D, and then also solve for Kc. So in this case, again, we can start with, now the way that I personally like to do these is, again, I like to split the reaction into two sort of quote unquote irreversible reactions, even though it is a reversible problem. Using the equation 319, you can actually just skip to the rate law, but I'm gonna sort of work this out long form. And the reason is because when I first learned this in both undergrad and grad school, actually, relearned it in grad school, the teachers tend to just sort of skip to the general form, but it helps me personally to remember that the rate law of a reversible reaction is equal to RF minus RR if I'm constantly just thinking of this in terms of a forward reaction and a reverse reaction. But certainly if you can skip to the general form, just do that. And so we split this reaction into two different reactions here, the way that I'd like to do it. And we can then define each of those independently RF and R sub R. 2A plus B. And so here, using the elementary rate law general form that we learned in last class, we can say that RF here is going to be equal to K sub F, CA squared, CB to the first power. And then R sub R is going to be K sub R times C, the concentration of C to the first power, and then the concentration of D to the third power. Now again, this KF and KR, moving forward, I'm not going to keep writing those, because when we introduce the form of KC as the ratio of KF to KR, it's assumed that any lowercase f you see is going to be the rate constant for the forward reaction. So when I write the rate law here, I'm going to be dropping the F and R subscripts. So here, using the general form from equation 3.19, we can write the rate law for this reversible reaction as K times, in parentheses, CA squared, CB to the first power, minus C sub C to the first power, and concentration of D to the third power, divided by Kc. And again, this K here is implied to be K sub F, but I won't be writing that anymore. Okay, so relatively quickly, we can come up with a rate law for the reverse reaction here. And then from previous equation, we can also determine the individual rate laws for individual species A, B, C, and D rather easily. So previously we learned that the rate of the overall reaction is related to the rate of the individual species by their stoichiometric coefficient. So it looked like something of this form. And in the general case, you can write it as R sub I divided by nu sub I, of course. So writing this out is relatively easy. So we can say that R sub A is going to be equal to nu sub A times the R that we already found, the rate law that we already found for the reversible reaction. And so this is going to simply be -2. Keep in mind that the stoichiometric coefficients for the reactants are still going to be negative. So in this case, it's going to be -2 times K, oops, lowercase k, K CA squared CB minus CC CD cubed over KC. And then continuing, we could do the same thing for the other species. So RB is simply going to be nu B times R. In this case, again, it's a negative, but the stoichiometric coefficient for B is 1 or -1. So we're going to get -K times the same thing here. And then the last two are going to be the same thing. I'm only going to write the C, the one for C, but you can do the rate law for species D relatively easy on your own. But this one is going to be nu C times R. And again, keep in mind that in this case, C is a product. So C, the stoichiometric coefficient for C is going to be a positive. In this case, it's +1. Yeah, +1. So we're just going to get R sub C is actually just equal to R, or the same thing that we had previously. Okay. And then the last part of this is going to be to solve for Kc. So as I already mentioned, the general form of Kc for an equation, for a reversible equation, is simply going to be the concentrations of the products raised to their stoichiometric coefficients, divided by the concentration of the reactants raised to their stoichiometric coefficients. So in this case, it's fairly easy. It's just going to be C to the power of 1, CD to the power of 3, CA, I believe, was to the power of 2, and then CB was to the power of 1. And so this becomes our answer for that part. So not too bad at all. Fairly easy, but yeah, not much else there. So the as I previously mentioned, there is a relationship between Ka and Kc, and that relationship is going to be dependent on the state of matter our system is in. So one thing I wanted to pull up here is recall that Ka is equal to the product from species A to Z of the activity A sub I to the power of its stoichiometric coefficient. If I recall correctly, I think this was equation 2.30. And then our new equation for Kc generally can be defined as the product from species A to Z of Ci to the power of nu I. And this one is equation 3.20. So if we're going to write any relationship that connects Kc and Ka, if you remember from table 2.1, which I will pull up right now. Table 2.1 defines A sub I, the activity, depending on the state of matter you're in. So for example, if you are in a ideal gas state, then AI is equal to P sub I divided by P naught. If you're in a pure liquid state, A sub I is simply the mole fraction of the liquid X sub I. So what that means is that any relationship that connects Ka and Kc has to be dependent on the state of matter, because Ka is dependent on the state of matter. And so we can write a relationship, or two relationships, one for liquids and one for gases. I suppose technically you could also do one for solids, but we don't really deal with solids. And so here, for liquids, this is so both the sort of derivation for liquids and gases can be found in your book on page 92 and 93. So derivations on page 92 and 93. And so I'm not going to go, they're really short derivations. I'll probably just do the one for liquids, and then you can look at the ones for gases. Basically, we start with knowing that the concentration C sub I is equal to the mole fraction times the total. Here again, CT, in case you forget, is the summation of individual C sub I's. And starting from equation, again, 320, we know that K sub C is equal to the product of C sub I to the power of nu I. Making a substitution in for the definition of C sub I written above, I'm sort of skipping some steps here, but this is going to be equal to the product of xi times the product of, excuse me, xi to the new I, times the product of ct to the new I. And then this can then be written as, because this here, in the case of liquids, is simply Ka, since in the case of liquids, the activity is simply the mole fraction of the liquid. This is simply Ka, times what will simplify down into Ct to the power of, I think this symbol is delta, where delta is equal to the summation of nu I. One thing I did want to point out is that if you do look at the derivation of this on or in your textbook, there is, and assuming you have a hard copy, there is a error in the format of the equation on page 92. At the bottom of the page, it shows the expanded form of Ct to the new I as being equal to CTA, CT B, CT negative C, and CT negative D. This is an error. So the negative should be on the A and the B, not the C and the D. So the correct form is going to look like negative A, negative B, positive C, and positive D, which is going to be equal to CT delta. Yeah, I think that's correct. So so just be aware of that. This is on this. This is the correct form of what should be at the bottom of the page on page 92 of your text. Question, is CT usually given? If it's not given directly, we might just give you the individual C sub i's, and then you can calculate it using this equation up here. Okay. And now, so this is the equation that we're going to be using for liquids. So let me highlight that. And then I'm not going to go too much in depth with the derivation of the gas phase reaction because it's very similar to the liquids. There's only like one extra step that's sort of for gases. There's only one sort of extra step that's like just an extra algebraic manipulation. But in this case, we're starting with the assumption that, or knowing rather, not the assumption that P sub I is equal to the concentration times the ideal gas constant and temperature. And again, starting from the equation 320, we can then derive an expression for Kc relating Kc and Ka in the gaseous state. And this simply becomes P naught over RT delta here. And so the kind of situation where these relationships are going to be useful is if you have a reversible reaction and you were asked to solve for like the previous example, we can solve for the rates and the rate laws for individual species. And then we can be asked for Kc and then the corresponding Ka. extend this page. Okay, so now knowing this information, we have a relationship between Kc and Ka in both the liquid and the gas state. So we can work through another example. Whoops. So here we have an equation 1/2 A plus 2B in a reversible reaction with 2C. Now, one thing I wanted to point out here to sort of emphasize also is that there seem to be a lot of questions about the definition of elementary reaction and elementary rate law. As Dr. Drews mentioned, almost every equation, unless otherwise specified, is going to be what we call elementary reaction. And what that means is simply that we assume it happens in one step. It has it doesn't necessarily have any relationship with the stoichiometric coefficients in front. That being said, though, it is also important, as Dr. Drews displayed on, I believe on Wednesday, that when you're given the stoichiometry of a particular reaction, and you're told that in all of these examples I'm giving that assume elementary rate laws, that it follows an elementary rate law, do not change the stoichiometry. So don't multiply this whole thing by 2, because if you did that, you'd get a separate rate law, and then you'd get a separate value for K and among other reasons. But essentially just leave it the same. Don't change any of the stoichiometry. And again, just because there is a 1/2 here, that does not mean that it's doesn't follow an elementary rate law. We're just going to assume that it does. So just like before, I want to know, oops. So I want to find R, R sub A, R sub B, R sub C, Kc, and then also in addition to that, find Ka, assuming the liquid case and the gas case. So we're going to do both of them separately. So just as before, like I said, I do like to, my personal preference is to split this into 2 reactions. So here we get 1/2 A plus 2B goes to 2C, and a second reaction that goes 2C to 1/2 A and 2B. And so here again, we have we're going to have a forward reaction and a reverse reaction. And so the total reaction for, the total rate law for the reversible reaction is going to be the difference between those two. So the forward minus the reverse. In this case, using equation 3.19, we know that the general form of it is going to look like K times, in this case, C sub A to the power of 1/2 C sub B squared minus C sub C squared over Kc. From there, we can find the rate law for the individual species. Oops. And using the relationship with their stoichiometric coefficient. So in this case, it's going to be R is equal to RA over nu A. Therefore, we can define RA as equal to nu A times R, which in this case is going to be, keep in mind there's a negative 1/2 in the front. Oh, yeah, sorry. This should be R sub R, not R sub F. Thank you. And so, where was I? The rate law for species A. So it's going to keep in mind that this is going to be negative 1/2 because of the stoichiometric coefficient on the reactant side. And so here we're going to get negative 1/2 times K, Ca to the 1/2, Cb squared minus C sub C squared over Kc. Similarly, we are going to get new B times R. In this case, it's going to be negative 2 K, and then the same reversible rate law here. Ca to the 1/2, Cb squared minus Cc squared over Kc. And then in this case, we only have one more, so I'll just write it out. This is going to be, because this is now on the product side, we have a positive new coefficient or stoichiometric coefficient. So it's going to be 2k, lowercase k, times Ca to the 1/2 Cb squared minus C squared C over Kc. Okay, and then next step is to find Kc. And so just like before, Kc is going to be equal to, in this case, Cc squared over Ca to the 1/2 and Cb squared. So that, again, that comes from equation 3.20, the general form. And then from there, we can, the final step is to find Ka, assuming liquid and then assuming gas. So in the liquid case, if we look back to our equations, we have, this is equation 3.22. Kc is equal to Ka times Ct delta to the power of delta. And then we can simply rearrange this equation, assuming we knew the concentrations such that we can actually derive a numerical number for Kc. We would then be able to rearrange this equation such that Ka is equal to Kc divided by Ct delta. Now, one thing that I did want to, I think I forgot to point it out previously, is that in this form of the equation, just be aware of the units of Kc in case you had to solve for either Kc or Ka. The units on Ka, are dimensionless. And then from this equation, which is equation 3.22, the units on Kc depend on C sub t to the power of delta, where it could vary based on the value of delta. So if C sub t is, for example, in units of, hypothetically, if C sub t is in units of moles per unit volume, if delta is negative, you might have to switch that. So because C sub t is raised to the power of delta, if delta is negative, you're going to have to flip the units on that. And then the units on Kc would be flipped as well. So here we have a simple expression to define the value of Ka, given if we knew the values of Kc, C sub t, and delta. And in this case, we can actually derive delta real quickly. So in this example, delta is going to be 2 minus 2 minus 1/2. So in this case, delta is equal to negative 1/2. So question, if you had more than just C in the products, would you just include that in the number for the Ka calculation? So if you had more than C in the products, so like if you had, if D was also a product, your Kc value would change. So if D was a product, Kc would equal to C sub C squared, C sub D to some exponent, whatever it might be, C to the A1/2 and CB squared. And so the change in the Kc value would change your Ka value. Yeah. Okay. Now, in the last case here, we have to solve what would happen if we had a gaseous state. So find Ka, assuming gas. So question, what would be the process if our Ka equation had partial pressures? Okay, I haven't gotten to that yet, but that's going to be at the end. And so Ka, assuming gas. Now, the way that I'm going to write this and the way that we had already derived it to sort of answer your question a little bit further is that this is still going to be in terms of concentrations. But at the end, I'm going to show you the equivalent expressions, but using partial pressures. So another question, would it change your Ka value though? You just mentioned that it would change Kc. You didn't mention Ka unless you meant to write Ka because you were. So yes, it would change your Ka value because Ka is, in this case, dependent on Kc. So if Kc changes, Ka changes, yes. Okay, so in the gas state, we had equation Kc is equal to Ka, no problem, Andy, Ka times P naught over RT to the power of delta. And this was equation 325 that we derived up above, or sort of derived up above. If you want the derivation in more depth, it's on page 93. But so using this expression, and we can again rearrange this for Ka, such that Ka is simply going to be Kc times RT over P naught to the power of delta. And here again, I do want to emphasize the units on Ka are dimensionless. And in this case, it's a little bit more sort of tricky because if we're looking at equation 3.25 here, because Ka is dimensionless, Kc, the units of Kc are dependent essentially on the units of P naught over RT. Keep in mind that P naught in this case is the standard pressure. So in our book, it's going to be 101.325, I believe, kilopascals. And but there's also still a delta value here. So again, if delta is negative, you're going to have to switch the units to be, you know, the reverse of P naught over RT, whatever that might be. And so, yeah, we end up with this expression here. Ka is equal to Kc times RT over P naught to the power of delta. And just like in the previous example, if the substituents of the reactants in this, of the reaction in this case were given as gas, you would use this equation down here. And again, delta is equal to -1/2 in this case. Okay. So the last thing I want to mention here is that if you recall, so when Dr. Drews derived the elementary rate law for a reaction such that AA AA plus BB goes to CC plus DD. In this case, he mentioned that the rate law can be written using concentrations, or it can be written using partial pressures. So in the case of writing it with, if you were to write it with partial pressures, there's an equivalent expression to derive the reversible reaction using partial pressures as well. And so the general form of that is going to be written as K times P partial pressure of A to the power of A, partial pressure of B to the power of B, minus partial pressure of C to the power of C, partial pressure D to the power of D, over K sub P. And notice here I use K sub P, not K sub C, again, because we're doing things in terms of pressure. So this equilibrium constant is going to be different than K sub C in terms of the value for a given reaction. And so in this case, K sub P, similarly to K sub C, is simply going to be, for this general case, is going to be P sub C to the power of C, P sub D to the power of D, over P sub A to the power of A, and P sub B to the power of B. And the shorthand notation for this is similar to K sub C, is going to be I equals from A to Z, P sub I to the power of nu I. So if you're using your reaction or you're writing your rate law for some reason in terms of partial pressures, if you're asked to, these would be the corresponding equations that you would use. And so this is equation 3.26. Seems like both of these are labeled, or they're both kind of under 3.26 on page 94. Okay, and so the last thing I wanted to point out too, this is sort of just for your convenience. I think this is going to be the end of material because we're almost out of time here. But table 3.1 in your book, I'm going to try to pull it up right now. But table 3.1 sort of summarizes all the different rate equations for whether you're using concentrations or partial pressures. And it'll be a useful reference. So this here is table 3.1. It's on page 94 in your book. And this will be a useful reference, similar to what we had for table 2.1. So that's going to be the end of material. If you have any questions, feel free to send them in now. So question here is it P naught? Is it P naught because equilibrium reactors take place at atmospheric pressure, thus P naught is equal to 1 atmosphere? So I think you were referring to this equation 3.25 up here. And correct me if I'm wrong, but I think this is what you're referring to. So the P naught actually comes out in the derivation of the equation itself. So if you look to page 93, P naught comes out in order to do a substitution for Ka. So I don't think it necessarily has anything to do with equilibrium reactors being done at atmospheric pressure. So this is a question about the homework. How do you estimate the equilibrium conversion without knowing the inlet outlet? So I think you might be referring to, I think it's question 4. There was a note added on to the homework. I don't know, maybe you missed it, but there was a note adding on that, or there should have been a note added on saying that you were to take the inlet as I think 1 mole per second. But someone can correct me if I'm wrong. Oh, speaking of homework questions too, if I don't know if you guys saw it, but my office hours have been updated on the syllabus earlier this week to be Tuesday and Thursday from 12:30 to 1:30. So if you do have any extra or more specific questions about the homework, you can feel free to hop into the Zoom call that's listed on the Canvas page and ask me then. This last week, it's been pretty lonely, so if you want to come in and say hi, feel free. Yeah, so I got confirmation. There's a note for that on Canvas on the homework assignment page. Can I show my Aussie when there's no more questions? Sure. So question, does pressure affect the value of the equilibrium constant Ka? So in the case of a gas phase, yes, it does, because we're looking at so in equation 3.25, if I rearrange solving, or actually, excuse me, that the pressure there is just the standard pressure. So if you mean pressure as like the reactor pressure, I don't believe so. I don't think Kc is dependent on pressure either. So no, it shouldn't be affecting Ka. Ka is only a function of temperature. No problem. So lecture is officially over, but I'm going to be hanging out here and asking questions, or answering questions, sorry, asking questions, answering questions. And as soon as my dog wants to cooperate, I can show her on camera. But she likes to lay down and doesn't like being picked up, so we'll see. This is Jenny. She does not like to be picked up and just kind of lays around, but yep. She's just falling now. So question, when does the equilibrium constant factor into making an equilibrium reactor? What value must it approach, or rather, what should it be to establish the desired equilibrium level, if that makes sense? So I think to answer your question, you can't really make an and correct me if I'm wrong, Dr. Drews, but equilibrium reactors aren't realistic in the sense that in order to truly achieve an equilibrium reactor, you'd have to have a reactor like of infinite size, essentially. But to answer your question, what value must it approach, or rather, what should it be to establish? So the equilibrium constant is simply a constant that's used to sort of define the upper limits of what your reactor could establish, because you can't do better than equilibrium. And so, like, let's say that the equilibrium conversion of a particular system is, I don't know, 60% conversion. You use the equilibrium constant in order to determine that, okay, you can't really go past 60% if that's where equilibrium is at. And ideally, you just want to sort of get as close to the equilibrium conversion rate as you could. And sort of all that information is inside the equilibrium constant Kc. Question, is there a relationship between Kp and Ka? Yes. So if you go down to table 3.1, this here is the relationship, the last one. So Kp is equal to Ka times P naught to the delta. Okay, I'll stick around for another minute or two to answer any more questions. It seems like most people are leaving now. Okay, I think that's we can end it here now.